So we are going to do this a little out of order. We're going to do page 4 first, and then go back to page 5, and then to page 3. So inscribed angles are different than what we were doing yesterday. The previous video showed a circle, and then there was a center point, and then the angle on the center was called the central angle. And let's say that central angle was 60 degrees, the arc was equal to 60 degrees. So an inscribed angle is where the vertex is actually on the side of the circle. And I'd like to start with the second one over here. Okay, if you look at BC, it appears like it's half a circle. So the arc is 180 degrees. If you follow it in, that angle, that's that inscribed angle that kind of makes it with its two chords, doesn't look 180 degrees anymore. If you look at it, it looks more like 90 degrees. And that's the rule for the connection between arcs and inscribed angles. If the arc is something like 44 degrees, then the angle inside there, the inscribed angle, would be half as much. And the same thing holds true if that angle is about 45 degrees. You'd need to double it to get to the arc. So that's why we have Theorem 10, a measure of an inscribed angle of a circle is equal to 1/2 the measure of its intercepted arc. And that means where these two chords, that's what they're called when they're segments in a circle, cross through and hit through here and leave through there. That's the intercepted arc. An angle inscribed in a semicircle is this example right up here. That's a semicircle. The inscribed angle is a right angle. And then I just have some examples down here. You may want to pause this and start looking at it yourself, but definitely come back to make sure that you're getting the correct answers. Usually number 1 people don't have a whole lot of trouble with because they follow 68 out. And the inscribed angle you need to double to get the arc. So that's about 120, 136, I believe. And then they always follow the 72 in. So if the arc is 72, then the angle is half as much. And then there's a couple different ways you can go about it. A circle has how many degrees? All the way around. 360. So 72 and 136 subtracted from 360 will give you this arc over here. Or if you look inside, you've got a triangle. And a triangle has to equal 180. So 68 and 36 and some angle must equal 180. So I'm going to try this one. If this is 68 and that's 36, when you add them together, you get 104. Take that away from 180, and it's like 76 degrees for this angle in here. And I like to think of circles as kind of puzzles. So if you were to take 360 degrees, if I've got 72 for this arc, and I've got 136 for this arc. If I subtract them from 360, I believe I get like 152. If I put 152, I can actually check it. That's my arc, cut 152 in half, and you get 76. So another way to check it. This example 2 is the one that people seem to have the most difficult time with. And I hope you realize that this is a center point right in the center here. There's no angle like this from previous lesson. And that's not making this part right here is actually not making an inscribed angle either. So just because this guy's 101 doesn't mean this is 101. Because vertical angles would make that 101. And this one across from it sure isn't 101. So just work with what you know. Follow out the inscribed angle that you do know. Remember to double it. If it's 39 degrees on the inside, it's 78 on the outside. So a lot of people will pretty much be stuck at that point. But there's a lot of different things that you could do. You actually could follow that 78 into angle C. Angle C opens up to arc AB as well. So angle C should be half of 78, or 39. If this angle is 101, the one across from it is 101. We were just talking about vertical angles. And these are still two triangles. So if that one's 101 and 39, take that away from 180. We should be left with like 40. Same numbers here, so this guy's going to be 40. And that should check because they both open up to this arc over here, which means that that arc should be 80. Now then becomes in question is, what's arc BC over here? And you've got 360 degrees. Take away 115, take away 78, take away 80, and see what you're left with. I believe when I did the math it was 87. And it does look significantly smaller than this arc over here. We will learn these angles coming up in a follow-up lesson about the connection between them. So you might even be able to see what the connection is between the numbers 115 and 87 to get 101. Maybe not. And we'll look at that in the future. So take a minute at example 3. It kind of uses all three things, or all both ideas. Central angles, so like this is a central angle, which means this arc must match it. And it also uses inscribed angles. So if that's 66, and I follow that in, this angle should be 33. And then we could work from there. Vertical angles over here tells me that this guy is 66 as well, and that arc is 66. And if that arc is 66, then that angle should be 33. Now I also can figure out the one next to the 66. It makes a straight line with it. So 180. Take away 66 should be a little bit smaller than 120, maybe 114. And we can even check and make sure that 33 and 33 and 114 make 180 degrees because it's a triangle. These are both radii or radius, which explains why those two angles are the base angles of that isosceles triangle. A lot of these things are connected. If that's 114, the one across from it, vertical to it, is 114, which makes this arc 114 and that arc 114. And then we can even follow the 114 in to get angle D. What's 114 cut in half? About 57. This 114 cut in half, that guy's 57. And we can check to make sure 57, 57, and 66 are making 180. And these are radii. So these base angles should be the same. And then take a minute to try to figure out and be able to label things with three angles, or with three letters. So angle AOB would be this 114 one. COB would be this 66 one. COD is at 114. DAO is the 57. ODA is the other 57. OAB, that little 33 up there. OBA is this 33. Arc AD, 66. Minor arc AB, 114. Minor arc BC, 66. And minor arc CD, 114. I'd like to skip the page then to the next one, and we'll talk about proofs using circles. If I don't introduce them when we learn them, they're difficult for students. So I do want you to fill out this one, and we'll go back to page 3 as well. So this is saying that these are chords, which means they're just segments in a circle that go from one end to the other. Keep in mind that this is the center point. Nothing's crossing through that. So I asked you to prove that they're similar, which means show that there's two angles the same. So in AEC, this one off to the side over here, I can tell it's got a similar angle vertical to it right over there. That's going to be one of my angles. In my other angles, we got to get creative. So if you think about where A opens up to, it's the same place that D opens up to. So start your statement and reason chart. So to prove the angles are the same, we're going to first talk about those vertical angles. Don't call them angle E. Put numbers in them or address them by 3 letters. We need to actually look at these angles specifically. CEA would be this one on the left. BED is the one on the right. And we need something about vertical angles. And we also talked about these angles at A and D. So if you look back at those definitions, some of the key things that we talked about in the previous paper or the previous page was that an inscribed angle is half the measure of its intercepted arc. So if both the inscribed angles are the same, then the arc should be the same as well. Now, if they both lead to the same arc, give a description. Both inscribed angles, it's always good to add in vocabulary, intercept, if we're trying to use the correct word for where they cross at BC, and we're talking about arc BC. Therefore, they are congruent. And if we've got two angles, then we've got similar triangles. So 1 check mark. We talked about this 1 time, 2 times before. To get this cross multiplication, we want to set up a proportion with these sides. So like CE and ED, BA and EA. We want to use those sides to set up a proportion. And you can do this many different ways. I'm going to pick like CE corresponds to this one's BE. And if I started with CE with this left one, I got to go AE for the right one, or for the left one, and then the right one, ED. So similar triangles, what do we know about their sides? Sides in proportion. And how did we get out of that? We cross multiply. So that's pretty advanced of a proof, but I just don't want you to get used to easy proofs. I want you to be able to see them used in many ways. Go back to page 3. There's a couple of things. If we talk about this one over here, up here, if this arc is x plus 60, this arc is x plus 60, again, because it's a central angle. And if this is x, in order to equal that, x plus 60, you got to double it. And then they're both pointing at the same arc. This arc must be 2x. It also must be x plus 60. So how much does x have to be to make both of those work? That's why we're doing this equation. If x is 60, then when you double it, you get 120. And if that angle, that central angle, is x plus 60 and 60 plus 60 is 120, that arc across from it is also 120.